In this video, we're going to be taking a look at the differentiability of our graph. Now, we've been asked to take a look at the differentiability of our graph when x is minus 1. So we are focusing particularly on this point over here. In order to test this differentiability, we must ascertain that our graph is already continuous. Now, there are three things that I need to do because it's a split graph. I need to check that f at minus 1 exists and that it's the same as the limit as I tend towards minus 1 from the left or from the right of the graph. So let's do that first. So f at minus 1, I can see I must substitute into the expression 2x plus 3. So that's going to be 2 times minus 1 plus 3. In other words, f at minus 1 is going to give me an answer of 1. Let's now check our limit. Remember, as I tend towards minus 1 on my domain, either from the left or from the right, in order for that limit to exist, it must arrive at the same height. So the limit, as x tends towards minus 1 from the left, is going to use the expression 2x plus 3. Well, we've already calculated that would have given me an answer of 1. Let's now test it from the right. So as x tends towards minus 1, coming from the right means that I would have to substitute into minus x squared plus 2. When you put minus 1 in there, you're also going to get an answer of 1. What we have done is we have successfully proven that our graph is continuous. When we want to test differentiability, we do a very similar process. For differentiability, though, I must make sure that my graph, in addition to being continuous, has a derivative from the left or from the right that tends to the same height. Let's check and see. If I take the limit as x tends towards minus 1 from the left of the curve and then look at the derivative of that curve, that answer must be exactly the same as I take a look at the limit as x tends towards minus 1 from the right of the curve. In other words, if I take a look at it from the left, then I'm going to find the limit as x tends to minus 1 of the derivative of 2x plus 3, and that is going to be 2. Well, there's no x for me to substitute into over there, so the answer is going to be 2. If I do the limit as x tends towards minus 1, but from the right, I have to substitute into minus x squared plus 2's derivative, which gives me minus 2x. Now, if I put in minus 1 in the place of x over here, I'm also going to get an answer of 2. As my graph was continuous because the point at minus 1 existed, the limit that I reached to, approaching minus 1 from the left or from the right, arrived at the same height. And it was also differentiable because the derivative of the curve from the left is equal to the derivative of the curve from the right. Just quickly though, I want to explain to you how a graph can be continuous, but it is not always differentiable. So in this graph, we're going to take a look at a couple of points that are not differentiable. Can you see that as my graph tends towards when x is minus 1, from the left or from the right, I'm going to arrive at the same height of 3. But as there is a hole at 3, there is a limit at 3, but it would be impossible to find the derivative there because f at minus 1 does not exist. There's a second place here where I could in fact had continuity because my graph is perfectly continuous when x is 2. But 2 is a sharp point, and I call that a cusp. If I have a cusp, I cannot find the derivative. If I just drew in a random tangent over here so that it touched my graph when x is 2, how would I know that that is correct? The moment that you think it's right, I would draw in another, or another. And so you can see that there is no derivative at x is equal to 2 on a graph that has a cusp. So if there is a hole, or a jump, or a cusp, I will not have differentiability in a graph.